Hello everybody, it's Mrs. Pound, and we are studying Chapter 11 on Chemical Calculations from BJU Chemistry's 5th edition. Today we're going to take a look at Section 11.3 on real-world stoichiometry. So we're going to look at how do chemists really use stoichiometry to do calculations. Our objectives today will be to identify the limiting and excess reactants in a chemical reaction when given the quantities of the reactants, and calculate the amount of excess reactant in a chemical reaction when given the quantities of the reactants, and calculate the percent yield when given the actual yield of a chemical reaction. So the first thing we need to know is what a limiting reactant it is. It is a reactant that is used up before the other reactants in a reaction, preventing more products from forming. Because let's face it, we're really careful to measure things out, but we're going to have a little bit less of one thing than another when these things are reacting. The excess reactant is the leftover substance that did not react because another reactant was completely used. So an example of a problem is lithium hydroxide canisters used on the space shuttle capture exhaled carbon dioxide gas and convert it into lithium carbonate and water. If a set of canisters contains 5,750 grams of lithium hydroxide and each of 6 crew members exhales 21 moles of carbon dioxide, will the lithium hydroxide canisters be a limiting reactant for that day? There's a lot of information here, but remember, we're doing stoichiometry, so the first thing you need is a balanced equation. So let's just look at that part of the problem. And that part says lithium hydroxide canisters used on the space shuttle capture exhaled carbon dioxide gas and convert it into lithium carbonate and water. So here we can see that the reactants are lithium hydroxide and carbon dioxide, and the products are lithium carbonate and water. So we will write that in our reaction like this. Now we need to take a look and ask ourselves, is this balanced? And if we look carefully at it, we realize it is not balanced because we only have one lithium atom over here and 2 over here. So we know that we have to put a 2 in front over there. So we have 2 lithium hydroxide now. And let's see if this is now balanced. So we have 2 lithium, 4 oxygen. So we have 4 oxygen over here, and then 2 hydrogen, and let's just check the carbon, carbon, carbon. So now this is balanced. So we have a balanced equation, so now we can take a look at our stoichiometric conversions. So let's look at the rest of the problem. It says if a set of canisters contains 5,750 grams of lithium hydroxide and each of 6 crew members exhales 21 moles of carbon dioxide, will the lithium hydroxide canisters be a limiting reactant for that day? Well, we always start with this value that they give us for the lithium hydroxide. And so we know that we have 5,750 grams of lithium hydroxide. And we have to convert that to moles of carbon dioxide. So in order to do that, we have to have a mole ratio. This isn't in moles, so we have to convert it to moles first. So we have to know the molar mass. And remember, we get the molar mass, this number here, by using our periodic table. Lithium is 6.94 grams. These are rounded numbers. Plus the oxygen is 16. The hydrogen is 1.01 to get 23.95 grams. So we do that conversion here. Grams goes on the bottom because it cancels. We're now in moles of lithium hydroxide. But we want to get to moles of carbon dioxide. So we need our balanced equation to get our mole ratio. And we see that for 2 moles of lithium hydroxide reacts with 1 mole of carbon dioxide. So here's our mole ratio, moles of lithium hydroxide on the bottom, so it'll cancel, moles of carbon dioxide on the top. So when we do that calculation, we get 120 moles of carbon dioxide. That is for all of the crew members. And we see here that we have 6 crew members who exhale 21 moles of carbon dioxide. So we have to multiply the 6 by 21, and we see that there is 126 moles of carbon dioxide exhaled, but only 120 moles can be captured. So our conclusion is yes, the lithium hydroxide is a limiting reactant because more carbon dioxide is exhaled that can be absorbed by 5,750 grams of lithium hydroxide. Remember, only 120 can be captured and absorbed, but 126 will be exhaled. So another question that might follow is, how many grams of excess reactant are there? Well, to know how much excess there is, we subtract 120 moles from 126 moles, and we get 6 moles of carbon dioxide. And I realize I forgot to put this in blue, but you should write that down. So the carbon dioxide, we need to know now the molar mass so that we can convert from moles to the mass. So 12.01 grams plus 2 times 16 grams, which is for the oxygen, is 44.01 grams. So we do our conversion. 6 moles is 1 mole on the bottom here, so that those will cancel out. Go ahead and cross those units out. And 44.01 grams of carbon dioxide is 264.1 grams of carbon dioxide will be excess. So we know now how to figure out limiting reactants and excess reactants. Now let's take a look at another calculation that chemists very commonly do, and that is percent yield. Theoretical yield is the maximum amount of product that could be created from a given amount of reactant in grams. That's what we've been calculating with our stoichiometry, our theoretical yields. But as you know, we seldom get everything out. So that is the actual yield, the measured amount of product at the end of a reaction in grams. And usually there's less than the theoretical yield because there are competing side reactions. Think of combustion. We do not usually have complete combustion. There are other side reactions. Not all the carbon dioxide is always created in combustion. You also have gases like carbon monoxide that are created. So incomplete reactions because there are side reactions. Reactant materials lost during the purification procedures. You just automatically lose some material. It clings to surfaces and other problems. Dissolved product is left on glassware. It's hard to get everything out. Liquid evaporated. Maybe you're trying to see how much water was created, but there was a little bit of heat and some of it was lost as gas. And limiting reactants prevented the product from forming. So just you didn't get as much as you thought you would because of a limiting reactant. So we calculate, because of this problem, percent yield. This is the percentage of the theoretical yield that was actually produced. It is an important indicator of efficiency for chemical manufacturing companies. So the percent yield is equal to the actual yield divided by the theoretical yield times 100%. So let's take a look at a problem that we use these equations. So a problem might be aluminum hydroxide is found in many antacid tablets because it reacts with hydrochloric acid from the stomach to form aluminum chloride and water. Now remember, we need our balanced equation. So we're going to take a look at aluminum hydroxide and we're going to make use of our oxidation numbers. So aluminum and hydroxide there, I have the oxidation numbers, and then hydrochloric acid, HCl, oxidation numbers there as well, forms aluminum chloride, oxidation numbers in water. So remember, we have to crisscross. These cancel, so we don't have to worry about that. But we crisscross here and we crisscross here to get this. Okay, so we have aluminum hydroxide, AlOH3 plus HCl yields AlCl3 plus H2O. So we have to take a look. Is this balanced? So we can look aluminum, aluminum. Okay, oh, one hydrogen here, 3 there. So that's 4 total. Oh, I only have 2 over here. So it looks like I have to balance some things. And Cl, oh, I need 3. So this can easily be balanced. We see that we needed the 3Cl here, so we put a 3 out front here, and that then gives us 3 hydrogen, 6. We only have 2, so put a 3 out front, and that fixes that. So we have aluminum, aluminum, 3 chloride, 3 chloride, and our OH3 and our 3, so that all balances. So then we can take a look at a problem like this. If 15 grams of aluminum hydroxide is found in a single tablet, determine the theoretical yield of aluminum chloride that would form if you assume there was an excess amount of hydrochloric acid. And a hint here, we're going to need to make a molar mass sandwich. So we need to know the molar mass of aluminum hydroxide and the hydrochloric acid. So I'm going to figure those out first. So aluminum hydroxide, that's 26.98 grams for the aluminum, 3 times 16 grams for the oxygen, and 3 times 1.008 grams for the hydrogen, for a total of 78 grams. Remember, we get all this from our periodic table. Aluminum chloride, 26.98 grams for the aluminum, and 3 times 35.45 grams for the chlorine, because there's 3 of those, for a grand total of 133.3 grams. So now that we have those out of the way, we're going to start with our 15 grams of aluminum hydroxide. And we know our molar mass. We've got to get to our mole ratio since we're doing stoichiometry to get to the hydrochloric acid. So we convert from our mass into our moles here. We have the 78 grams of aluminum hydroxide on the bottom, which is 1 mole. We then have to look at our equation here. And so we look at our equation and we see that the mole ratio for going from aluminum hydroxide to aluminum chloride is 1 to 1. So here's our mole ratio in the middle of our molar mass sandwich. And then on the other side, we have our molar mass of aluminum chloride, 1 mole on the bottom to cancel out our moles there. So make sure you're canceling out your moles. I know I forgot here, but cancel out all those moles to make sure you're in the right units. We're in grams of aluminum chloride. And when we do the calculation, we get 25.63 grams of aluminum chloride. Now, if 23 grams of aluminum chloride were measured in the products, calculate the percent yield. So this is the actual that we found. We just calculated the theoretical. So we take the actual, divide it by the theoretical, multiply by 100. So we take that 23.00 that they said we actually got, divide it by the theoretical of 25.63 grams, multiply by 100 and get 89.74%. So actually, this is a pretty good yield here. This is a good reaction. This will be well worth it economically for the company. All right, so our objectives today were to identify the limiting and excess reactants in a chemical reaction when given the quantities of the reactants, calculate the amount of excess reactant in a chemical reaction when giving the quantities of the reactants, and to calculate the percent yield when given the actual yield of a chemical reaction. Don't forget your 5 questions and your margin, and we'll be working on some more of these problems in class. Also, this is it for this chapter, so you have all the information you know to take the test.